Assalamualaikum warahmatullahi wabarakatuh and good morning to Dr. Jamil and friends. So today I would like to present about the assignment RTS BEEC 4834 real-time system. Yeah, so this presentation for chapter 7 real-time operating system. So there is the group 4 members. We have 5 members. For the first one is Yamuna. Number two is Nik Razi Naif, Muhammad Hairi bin Johari, Liu Wenrui, and Nur Syazwani binti Zainul. We go to the definition of RTOS. RTOS is stand for a real-time operating system. RTOS is an OS that guarantees real-time application a certain capability within a specified deadline. RTOS are designed for critical systems and for devices like microcontrollers that are timing specific. RTOS processing time requirements are measured in milliseconds, so any delays in responding could have disastrous consequences. So there's a characteristic of RTOS. So for number one is safety and security. Safety critical and security standards are typically the highest priority as RTOS are frequently used in critical systems. Number two is high performance. RTOS are typical fast and responsive. Number three, priority based scheduling. Tasks that are assigned a high priority are executed first, followed by lower priority jobs. And lastly is timing information. RTOS are responsible for timing and providing application programming interface. So there is the future of RTOS. So number one is scheduling. RTOS employ various scheduling algorithms to determine the order in which tasks are executed. Number two is interrupt handling. Real-time system rely heavily on interrupts to handle time-critical events. And lastly, inter-task communication. RTOS offer various mechanisms for inter-task communication such as message queues, mailboxes, semaphore, and share memory. So there is a comparison between OS and RTOS. So for the firstly, for the operating system is a software program that acts as the interface between the user and the underlying hardware of a computer or an electronic device. And then for the real-time operating system is specifically designed for real-time application. It is a specialized type of OS that provides quick and reliable response to input signals. Example of RTOS. So for the example of RTOS is airline traffic control systems, command control system, airline distribution system, herd pacemaker, network multimedia system, and robot. So that's all for me. Thank you.
Assalamualaikum and hi. I will continue to present for the next subtopic, which is interrupt. Interrupt is used for scheduling, asynchronous notification, and exception handling. It can occur in the hardware for signal external event like timer and in software generated by an instruction, for example, system's call. Next is interrupt service routine. An app consists infinite loop of desired operation like background. Interrupt service routines handle asynchronous event for foreground and critical operation must use in service routine to make sure timing correctness. And then memory management. Memory management is limited amount of memory. Fine-grained memory control should be possible. Memory allocation restricted to parts of real memory and general issue consist of heap management and stack management. In heap management, it used with allocators, key problems, which is how much space required, when the time allocated space can be released. Returning allocated space may require the programmer runtime to monitor and determine when it no longer can be accessed and runtime monitor and release when no longer being used. For stack management, it's important for embedded system. Specify stack size or tree. Calculate stack size are more difficult because task enter blocks and execute procedures can make the stack grow. Two, require knowledge of the execution behavior. And three, words that usage bound can be get from can be get from control flow analysis of test code. That's all from me. Thank you.
Good day, doctor and everyone. I'm Yamuna and I will present on scheduling. So the first scheduling is clock-driven scheduling. So clock-driven scheduling is a time-triggered approach where tasks are executed based on a fixed schedule. Next, each task is assigned a time slot or period during which it should execute. Next, the scheduler guarantees that tasks will execute in their designated time slots, ensuring determinism. And last is, this approach works well for systems with predictable task patterns and known worst case execution times. Next is round robin. So round robin scheduling assigns a weight to each task. Next, tasks are allocated CPU time based on their weights in a round robin manner. The third point is higher weighted tasks receive proportionally more CPU time. And the last is scheduling is effective for systems with mixed task types and varying resource requirements. So the next is priority scheduling. Priority scheduling assigns priorities to tasks based on their time requirements. So the first is rate monotonic scheduling, which is RMS. It assigns priorities inversely proportional to task periods. And the next is shorter period tasks have higher priorities. The next scheduling is earliest deadline first, which is EDF. It assigns priorities based on their relative deadlines of tasks. And the second point is tasks with closer deadlines have higher priorities. And the last scheduling is least slack time LST, which is LST. So the first point is dynamic priority scheduling algorithm. Okay, it is a dynamic priority scheduling algorithm. It also assigns priorities based on the remaining slack time of task. Slack time is the difference between the task's deadline and its execution time. So the tasks with less slack time have higher priorities. So this scheduling is suitable for aperiodic and sporadic task systems. Okay, next is priority based kernels. There are two types of kernels, which is preemptive and non-preemptive. Alright, so the first point is preemptive scheduling allows higher priority tasks to interrupt lower priority tasks. So mostly these preemptive is commercial real-time kernels are preemptive. So next is non-preemptive. This scheduling allows tasks to execute until completion without interruption. And then cooperative scheduling is a common non-preemptive scheduling approach where tasks voluntarily yield the CPU to other tasks. So this cooperative scheduling requires careful task design to avoid situations where a task hogs the CPU, which causing the system delays. And then now I will explain on the advantages and disadvantages of preemptive kernel. So the first advantage is execution of the highest priority task is deterministic, and the task level response time is minimized. So disadvantage of the preemptive kernel is should not use re-entrant functions unless exclusive access to this function is ensured. Next is advantages and disadvantages of non-preemptive. So the first advantage is interrupt latency is typically low. And then next is can use non-reentrant functions without fear of corruption by another task. This is because each task can run to complete before it relinquishes the CPU. So these non-reentrant functions should not be allowed to give up control of the CPU. Next is task response is now given by the time of the longest task. Alright, and the last is less need to gut shared data through the use of semaphores. So this point is where when we share input or output devices, this can still require the use of mutual exclusion of semaphores. So next is the disadvantages. So one of the disadvantage is response time is non-deterministic, where higher priority tasks might have to wait for a long time, and the response time is obviously non-deterministic. And the next disadvantage is very few commercial kernels are non-preemptive. And the last is resource management. This involves allocating and deallocating system resources efficiently. Resources can be categorized as shareable or exclusive, and different protocols are used to manage them. So examples of resource management protocols includes priority based, time based, and priority ceiling protocols. So that's all from me. Thank you.
Now we proceed to the semaphores. So what is semaphore? A semaphore is a synchronization mechanism used in real-time OS to control access to shared resources. It is a variable or data structure that maintains a count and a queue of tasks waiting for access to the resource. Roles of semaphores. So for mutual exclusions, semaphores ensure that only one task can access a shared resource at one time, preventing race condition and conflicts. So for task synchronization, semaphores allow tasks to synchronize their execution, ensuring a proper sequence or coordination. Let's explore the two common types of semaphores, binary and counting semaphores. So for binary semaphore or mutex, also known as the mutex mutual exclusions, so it has the two states, 0 and 1. So it's to ensure mutual exclusion, allowing only one task to access the resource at a time. For counting semaphore, allows a count greater than or equal to 0, represents a finite number of identical resources. Enable multiple tasks to access the resource concurrently up to the available count. Now let's understand the concept of the counting and the count value associated with a semaphore. Counting. A counting semaphore represents the availability of a specific resource. The count value signifies the number of available resources. A count value. When a task wants to use a resource, it checks the count value of the semaphore. If the count value is greater than 0, the task can access the resource. If the count is 0, the task will be blocked until a resource becomes available. And in this case, the count will increase. Now that we grasp the basic of the semaphore, let's explore the operation involved in this semaphore. So the first operation is the initialize. A value must be provided, and the waiting list is initially empty. And the next operation is the take, also known as the wait or P operation, used by a task to acquire a semaphore and access a shared resource. If the semaphore is available, means the count is greater than 0, the task will decrement the count and proceeds. If the semaphore is not available, means the count is equal to 0, the task is block suspend until the semaphore becomes available. The next operation is the give, also known as the signal or V operation, used by a task to release a semaphore or relinquish control over a shared resource. The task will increment the count of the semaphore, indicating that the resource is now available. If any tasks were waiting for the semaphore, the scheduler may unblock the highest priority waiting task. So that's it for semaphore.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Nurshadani binti Zainon. Here I want to present about Linux for real-time applications. Linux is powerful and versatile operating system. Real-time applications demanding strict timing guarantees and predictable behavior. Challenge of real-time applications were timing constraints, determinism, and lastly latency. Timing constraints, critical tasks must execute within specific time limits. Determinism, consistent and predictable system response required. And lastly latency, minimizing delays for timely task executions. Enhancing Linux for real-time capabilities, real-time frameworks and modifications enable Linux to meet real-time requirements. Popular frameworks include PreemRT-Patch, Xenomai, RTI, and PreemRT. Benefits of Linux for real-time applications were wide adoptions, open source nature, hardware compatibility, and lastly, vast software ecosystem. Applications areas for Linux real-time applications can be used in industrial automations to control system, robotics and manufacturing. And secondly, can be used in aerospace and defense for avionics, flight control system and simulation. And lastly, can be used in telecommunications for networking and real-time data processing. That's all for me, Nusha Zani binti Zainon.